Okay, so consider we have a function y equals f of x. So y is a function of x. Here, this is the x-axis, this is the y-axis. And here we have a point f of a, right? So this is the y value of this point. And our aim, so we talked about last time, I mean in that class, instantaneous rate of change versus average rate of change. And how do they differ? So if you take an interval and if you evaluate the slope of this line, which passes through 2 points, let's say any point x in here. So how would you find the slope of the secant line? You would get the difference of the y values, f of x. So just find the difference between the y values, f of x minus f of a, and divide it by the difference in x's. So this is just the definition of slope, right, of a line that passes through these 2 points. And this is, in fact, this gives us the average rate of change of a function, okay, of this function on the interval from a to x. And we use this fact to guess the instantaneous rate of change at a point. And what is that? So if you keep, and I will show you in a graphing calculator in a minute. So if you keep getting closer, if you keep picking x values that are closer and closer to a, so if those two values that you are using to find the slope of this secant line, so we call this the secant line that passes through these 2 points, and if you keep picking points that are closer and closer, eventually you will obtain an estimate for the slope of the tangent line. So let me just draw this line again. So those secant lines, if we keep picking x values that are getting closer to a, then we obtain the tangent line at a, okay, at x equals a. And in fact, it's gonna tell us, it's gonna give us the instantaneous rate of change of this function, okay? So this is what we have talked so far. Let me also mark, label this one. This is the secant line, okay? And it gives the average rate of change, okay? So the secant line has the slope given with this expression, and it gives us the average rate of change between 2 points. And if you want to talk about the instantaneous change at that point, you should make your interval smaller and smaller. So eventually it's gonna approach, so these secant lines will approach to the tangent line, which just passes through the point A. So realize that this point, I mean this tangent line, has only one intersection with the curve, although the secant lines have 2 intersections. Okay, so this is what we had taught. And in your homework, instantaneous is specific line. Instantaneous rate of change, yes, is the slope of the tangent line, okay, at A. Instantaneous rate of change is given by the slope of the tangent line, but however, well, in fact, it is just, it has one value, it is unique at that point. But when you talk about the average, you could pick different intervals, so you could have different secant lines. And you pick 2 points, so that gets closer, and that's going to give you the average rate of change, which is the slope of the secant lines, okay, that are defined with 2 points. And this is defined at only 1 point, one single point, okay? Okay, so we had discussed this idea during our first class, and we talked about the limits notation. We talked about numbers getting closer and closer to a value, and we talked about what does the function value equals at that point. So in fact, we can define the slope of this tangent line. So we were looking for the slope of the tangent. We were looking for the slope of this tangent line, and in your assignment, you were picking numbers that are getting closer to that specific point. And we are now going to write it formally. So this tangent line can be written using the limit notation. So the slope of this tangent line will be the limit of the slopes of the secant lines. So since the secant lines getting closer, they're approaching to the tangent line, the slopes of these secant lines will approach to the slope of the tangent line. So let's just copy this expression. We will just copy it here. So we can find the slope of this tangent line by evaluating the limits of the slopes of the secant lines as the x values get closer to a. Okay, so this is how we will be defining the derivative, and this is where the idea comes from. So today's take-home message will be just, this is the main formula you should learn from today's lesson. And the main idea is that we will call this expression the derivative of the function, and it's geometrically it means the instantaneous rate of change, and it corresponds to the slope of the tangent line. Okay, so this is the main idea for today's lesson. So again, today what we did was just to combine the two things we learned. So we learned that the secant lines approach to the tangent line as we get closer to that point, as we pick 2 points that are getting close to each other. And we just wrote the definition of the tangent line using the limit notation. Okay, so we just need to pick x values that are getting closer to a specific value a, and at that point this expression, which is the slope of the secant lines, will approach to the slope of the tangent line. Okay, let me get rid of this first. So far what we said was that we could, if we have a point a and it is function value f of a, then we can pick another value x on this curve, and this is going to be f of x, and we can find the slope of the secant line, so the slope of the line that passes through these points. How do we find it? This is just the difference of y's divided by difference of x's, and in fact we call this expression as the difference quotient. Okay, so today you will just learn some names. I don't know why this menu pops up. Okay, fx is the main function from the beginning, yes. So f of x is the main function that we are going to be finding the rate of change the average or instantaneous rate of change. Okay, so, and this is the slope, right? The slope formula for this average rate of change from between 2 points. And we give this a special name. We call this the difference quotient. So it is defined with this expression. Okay, I'm not going to be writing it formally. You can just find I mean, this is how it is defined. So you can also read the formal definition from the text. Okay, so we can also, I mean, in some cases, it's also useful to define the same thing. So we are going to be defining the same thing, but with a different notation. So consider you have this point A where you would like to find the instantaneous rate of change, okay, like the tangent line at the slope of this tangent line. And in this case, again, consider you are picking some numbers. So the only thing we are changing is the notation again. So consider you are just going h units away from a. Okay, so you are just picking this value, which is a plus h. So this is also another useful definition. So so you are picking at this point the x value, instead of calling it x, we just say this is a plus h, because we just moved h units. We just added h to a. And in this case, what is the y value here? Okay, yeah, we will see an example. Let me in fact show you here. So let's say you would like to evaluate the slope of this curve at x equals 1, okay? And in our examples, we picked points 1.1, 1.07, let's say 1.02, right? So you were just picking numbers that are getting closer to 1. So if you use this x notation, so in this case, your a is 1 in both cases, right? Your a is 1. And if you use x notation, you are picking numbers 1.1, x equals 1.07, x equals 1.02, right? Which are getting close to a. And if you use the h notation, so in this case, you are just choosing h to be 0.1. You are choosing h to be 0.07. You are choosing h to be 0.02. So in the second notation, h represents the difference between the x values. Okay, it is just the distance between the 2 points that you are picking. Yes, I'm using, yeah, in the second notation, we are using h instead of x, but they are not the same thing, right? So in fact, h, if you want to relate the two things, is simply x minus a. Yes, it represents the difference between h and a. Sorry, between x and a. Okay, so, well, you could call this point x, right? A plus h, so this point is x, and h only represents the distance. So the small number that we are adding to a. Okay, is it clear now? Okay, so I will delete these for now, so you got the idea. So h is simply what we are adding, the small distance between the 2 points. In fact, again, here, instead of x, we just use a plus h. So h shows, represents the distance between a and x. Okay, so here you have the same distance h here, but in the first notation, we only use a and x. So we will just define the same thing, but only the notation will change. Okay, so can I erase now? Okay, so I think my computer is getting old. it's very slow today. Okay, so we can define the slope of the same line, the secant line that passes through these points. Now, instead of f of x, what should we evaluate? So we will just use f of a plus h, right? So because this point is now what we call a plus h, so because we added h to a, so we should evaluate the function at f of at a plus h and subtract f of a from that. So the rest, like this is the same expression. And what do we divide by? So what do we have in the denominator? H. That's right. Thank you. H, because you are just subtracting a minus h and a, right? So a and a minus a plus h. So the difference between the two x coordinates, so a's will cancel out. It's going to be h. So you are just taking the difference between two x points. Okay, so these two definitions, they are both giving us the slope of the secant line, and we use them interchangeably. So in one case, it's more like convenient to use one definition. In another case, it's more convenient to use the other one. So this is also called the difference quotient. Okay, and they result. So the result is the same. So we just use different letters. Okay. So that is the same formula, same as other. Yes, those will end up. Yeah, those will end up with the same result, and we can just confirm it with some numbers. I mean, some examples. So now let's formally define. This is like short for definition. Which one is easier? Depends on the question, but maybe you might find the first one easier in when you're evaluating slope at a specific value, a value. But in fact, we will also need to make use of the second formula when we are defining the slope throughout, like for multiple points, I mean, throughout the whole domain. Okay, we will come to there, and we will see an example once we finish this definition. Okay, so the tangent line, and what was the tangent line? So the tangent line to a function f of x at a is the line passing through the point a, comma, f of a, okay, and having the slope okay. So here we are just, so again, we already talked about this, so we are just writing it, the formal definition. So the tangent line is the line that passes through a point A. And how do we find its slope? So we said that the slope of this tangent line equals the limits of the slopes of the secant lines. So we just copy the expression. We can use either of these expressions. So limit of f of x minus f of a divided by x minus a as x approaches a. Okay, so we had already defined this in the previous slide, in the previous whiteboard. So what's telling us? So this was, so remember, without the limits, this is the difference quotient, and this gives us the slope of the secant lines. If we take the limits as x approaches to a, okay, if we take this limit, then we find the slope of the tangent line. So this is the tangent line, be careful, not the secant line anymore. And alternatively or equivalently, you can use the other definition of the difference quotient. So we will take the limit of this expression. So in this case, we don't have x anymore. So the part of the equation is for secant and the whole is for tangent. Well, in fact, okay. So this formula, let me just mark for now. This formula is for the secant line, right? And which is equivalent to this part, the slope of the secant line. So if you take the limits of that expression, if you include this limit, this part in the formula, then you will find the slope of the tangent line. So the slope of the tangent is just the limit of the, okay, secant, limit of the slopes of the secant line. So let me see. The only thing missing here, that what should we, what is the, I mean, when we are taking the limit, which value is getting close to which value? So this is now what we should fill in this formula. So just consider the second definition of the difference quotient. So in this example, I mean, if we use this notation, what we are doing is we are getting closer to A. So as you get closer to A, what happens to the values of H? So in fact, we should take the limit as H goes to. So what's happening? Okay, so be careful here. Well, X is getting close to A, but in fact, H just denotes the distance between the 2 points, right? H shows the distance between the 2 points. So what is the value of H going to? Another try, so try again. No, remember, in fact, H is the difference between X and A if you consider the first description. Okay, so when I'm gonna write, you will understand that 0, because H represents the distance between the 2 points, and the 2 points are getting closer and closer to each other, right? X and A are getting closer to each other. So if you use this definition, you would just take the limit as H, which is the difference between those 2 points, go to 0. Okay? Does it make sense now? No. Okay, so let me just come back to here. Okay, maybe when we see an example, it's gonna be better. So in fact, the next thing is I'm gonna be writing an example, but so you also need to understand the idea. And I believe you did, so maybe you are just confused with this H thing. So let me just try to clarify that. So remember, let's say we are trying to evaluate the instantaneous rate of change at 1, which is going to be the slope of the tangent line at 1. And we are picking values 1.5, like 1.1, and so on. So just pick 2 points and just finding the slopes of those secant lines, right? So in the first notation, we are saying this is x equals 1.5, and we are x is getting closer and closer to 1. In the second notation, we just look at this difference. So in this case, we say that h is 0.5. H is getting smaller. H is 0.1. So realize that h is getting little and little. So we just take the limit as h goes to 0. Okay, so and another thing, in fact, you would just need to sleep and sleep over these ideas for them to place in your brains. So it's very important while you are sleeping. It's going to process, your brain is going to process these, and tomorrow you will have a better understanding, believe me. Okay, so that's why they say when you are preparing for an exam, you shouldn't just study that day, but at least a day before, so that you would sleep on it and your brain will process and you will learn better. Find the equation of the tangent line to the graph of x squared. Let me just say y equals x squared, or f of x equals x squared at x equals 3. Okay. So we will find the equation of the tangent line. Let me make a sketch, and in fact I will just show you on graphing calculator. So we find the value of y first. Yes, let's say yes. How would you find that? What do you mean by that? Or what do you mean by that? So this is the number 3. Oh, you mean you plug it into the function? Yes, that would make sense. Yes. So this is x equals 3, and what is f of x? 9. That's right. Yeah, that's a good point. Yeah, you could. Well, I mean, it's better to sketch a graph. Yeah, then you have your points. Well, you have 1 point, right? So we have just 1 point now. And to be able to find, well, this corresponds to A in our notation. And we would like to find the slope of the tangent line, which just passes through this point. I couldn't draw it perfect. Okay, so it only touches the graph at here. What is 6? Slope. Well, to be able to find the slope, remember we need 2 points, right? How would you find 6? Well, you need to pick 2 points on the line, right? And you would look at the y difference, you would look at the x difference, right? Delta y over delta x. This is how we define the slope. Okay? So in fact, is that clear so far? Okay, so consider we pick a point x in here. Okay, so we pick a point x, and this value will be f of x, which is x squared, right? So if you just call this point x, and its value will be x squared. So we just pick another x value. So pick this, which is going to be on the graph of f. So pick this value, let's say, or pick this point. And then let's write the slope of the secant line. How would you write the slope? So remember, it was difference in y's over difference in x's. With these 2 points, x and 3, how would you write what's in the numerator? Let's write the numerator first. So I'll just remind you the formula. It was f of x minus f of a. Okay, so the function is x squared, that's right. So x squared minus 9. Okay, so we just evaluate the function at x, at any general x value, and at the specific point that we are looking for. That's correct. It's divided by x minus 3. Okay, so this is the slope of the secant line. How about the slope of the tangent line? How do we find the slope at exactly this point? So which is slope of the line, which is tangent at that point. Now it doesn't pass through x anymore. So what do? We just take the limit. Okay, this is what we defined in the previous slide. We take the limits as x values, as the numbers we pick approach to 3, okay, of this expression, x squared minus 9 over x minus 3. Okay, so does it make sense? So we just want to find the slope of the tangent at 3, and we write the like we pick 2 points instead. We start with 2 points and write the slope of the line that passes from those 2 points. Then we say that if we get closer to that point A, if x's get closer to that point A, then the secant lines will approach to that tangent line. So this expression will give us the slope of this tangent line. Okay, so we learned how to do this calculation yesterday, right? So when you plug it in, the denominator is not defined, so we have to simplify this expression. We have to try to simplify. So yes, we can divide both sides by x. I mean, just factor out the numerator by x plus 3x minus 3. And that's right, we just cancel these out. And this limits as x goes to 3. Okay, so when you said 6 in the beginning, I don't know who said 6, but that was right. So Megan, I don't know how you said 6, but you had found the correct answer because, yes, okay. So when you plug in now, so once you have a polynomial, yeah, okay, that's right. So we will see that shortcut soon. So, I mean, now we are just like defining the derivative, and then we will be able to just come up with rules for each function so that we don't need to go through this definition all the time. Okay, so if you plug in 3 for x, then what we find is this slope is 6. Okay, so the slope of this line, the slope of this tangent line is 6. And the question asks us to write the equation of the tangent line. So we found its slope, and we know what point it passes through, 3 to 9, right? 3 and 3 squared. So just write the equation of the line that passes through this point and whose slope is 6. So what would be the equation? Well, you could just find the slope and, I mean, you know the slope. Yes, that's the formula I will use. Y minus the y value 9 equals m times x minus the x value x, is 3. Alternatively, you can just make use of y equals mx plus b. Here, just replace m with 6, y with 9, x with 3 to find b. You would end up with the same equation. Okay, so this is a formula. Okay, this is a formula which is very commonly used, so I just memorize it. And I mean, you could also remember that. So this is the formula: y minus y1 equals m times x minus x1. So this formula gives you the equation for the line, I would say for the line, which has a slope equal to m and which passes through the x1, y1 point. So there is a very easy formula to write down such equations, and again, it's useful. So you would immediately plug it into this formula. You know the slope, you know the point, so just plug it into the formula. And when you solve this formula for y, so it's going to be 6x minus 18 plus 9, you will find y equals 6x minus 9. Okay, makes sense. So let's sketch this on a graphing calculator and C. So the limit of the secant line equals the slope of the tangent line. Yes, exactly. Yeah. Okay. So let me take this here. The Desmos. I'm gonna open the Desmos driving calculator. Okay, so let me take it back while while it starts responding as I wait for it. Okay, so when do we use the formula, that formula? Well, you don't have to use it, but again, it's useful. So you want to write the equation, whenever you want to write down the equation of a line, given the slope and a point that the line passes through, you can make use of this formula. But you can also write it using, so I'm just going to put it here. Alternatively, how can you write down the equation? So you know that this is the slope-intercept form of any equation, of any line. And we know the slope is 6. We know that x is 3 and y is 9, right? Plus b. So you can just find b from this equation. Let's do that. 9 equals 18 plus b. So just subtract 18 from both sides. B equals -9. So if you write now, plug it back into this expression, y equals 6x minus 9, you find the same equation, right? So you find the same equation. So you can use either way. So are you more familiar with the second way? Yes, okay. So the first one is like another formula, and that's how I do it with that formula, but you can stick to your own methods, so both are fine, okay? So now let's graph both lines. I mean both graphs in here. So our graph was x squared, right? And we wanted to graph the tangent line at x equals 3, and we found y to be 9. And we found the equation to be 6x minus 9. So now you see, okay, I'll get closer. So the red one is the graph of the function, and the green one is the tangent line. So if you get closer, well, they overlap in here. Well, I mean, we won't be able to see that because it is like just evaluating it numerically. So here you can see that they are not equal, but in fact, they are, in theory, they are just touching at that single point at 3 to 9. Okay, so you see, although they seem to be overlapping in a bigger region, normally the green line just intersects at 3, 9. Okay, makes sense. In fact, I had just created another graph for us to analyze the relationship between secant lines and tangent line. Okay, and in fact here you see okay, I mean, you don't need to understand what I have on the left side, but the red one, the first line, is the graph of a function x squared, which we just worked on. And here, in fact, I wanted to find the tangent line at this point, at 1, 1. Okay? And okay, look at the green line. So green line is, they are the secant lines. Okay, so if as we get closer to the x point, we see that the secant lines approach the tangent line at 1, 1. So here, in fact, what we have here as the h is the same h we have in the formula when we used to define the difference quotients or the slopes of the secant lines. So let me just come back here. So suppose we choose the difference between the 2 points h to be 1, and then the green line, the secant line, will look like this. And if you just decrease the value of h, 0.9, 0.8, so we see that the two lines, sorry, the 2 points are getting closer. And at this point, when h is 0, we obtain the tangent line. Okay, does it any questions here or in the original question? So this is the same example. I just wanted you to see how the lines are moving as the 2 points are getting closer. Okay. Yes, that helped. That's good. Okay. So we talked about the tangent line, and we found the slope and equation of a tangent line for a function. So let's now formally define the derivative. Okay. So the derivative of f of x. So the derivative of a function at a, at x equals a. Okay, so we first define the derivative at a single point and denoted by f prime. Okay, so this is how we denote the derivative, and we will see other notations. In fact, I'll just check the book for other notations later. Is defined by okay, f prime of a, the derivative of a, sorry, the derivative of f at a is defined by what we have, by the same definition we used to define the slope of the tangent line. So the limits as x approaches a of f of x minus f of a divided by x minus a. Okay, so this is the definition of the derivative of a function at a. And equivalently, we can define the derivative of f at a using the h notation. So remember, h denotes the distance between 2 points. So we should take the limit as h goes to 0, it diminishes. So in this case, we just evaluate the function at a plus h minus f of a divided by h. Okay. So in the second definition, we don't have x, but we define it with h. Okay, in fact, I just realized that when we did the previous question, we only used the first definition, right? But we can also use the second definition. So we can practice it maybe in another problem, or maybe we can repeat that problem. We can come back to that. So what did we define in this definition, we just defined, we just said that we call this limit the derivative of function f at a, which is the same as the slope of the tangent line at a. Okay, the slope of the tangent line to the function f to f at the point a. So these mean the same thing, and the two definitions we give here are equivalent. Okay, so you can pick whichever you like. Okay, so let's go back to the previous question. I will just say find. So they both are. So both formulas are. They give us the slope of the tangent line to the function f at a, and they are both. They both define the derivative. Okay, so we call this the derivative. Did you read? You couldn't read somewhere? So, let's find the derivative of the function at x equals 3. Okay, so this is exactly the same question that we did before when we found the slope of the tangent line at 3. Okay, so we are now just I just asked the question in a different way. So this means, in other words, find the slope of the tangent line at x equals 3. Okay, these mean the same thing. So how did we do this in the previous question? We made use of this definition. So we said that the slope of the tangent line at 3 is going to be the limit as x goes to 3. So I'm just copying what we did before. X squared minus 9 over x minus 3. So remember, we just did this in the previous question, right? So we found this to be 6. So we've already done that. And to be able to find the derivative, you would do the same thing. Okay, you would just evaluate the same expression. Now, I just want to do using the second definition. Okay, would you like to do that? So you can compare which is easier. Yes, okay. So in fact, for completeness, let's copy those steps. What we did was we just factored this out and we simplified the x minus 3's. So we found the limit as x goes to 3 of x plus 3, which was 6. Okay, so we can use the first definition to find the derivative, which is the slope of the tangent line. Now, that's okay. So this expression is the slope of the secant line, but when you put the limit, it becomes the slope of the tangent line. Okay. So now, this and this, the two definitions are the same as we claim. So let's now use the second. So I'll just move it up. So let's use the second definition and see if we can find the same thing. Okay, so the limit as h goes to 0. Okay, so we will just need to use the second definition. Let me copy here and then we will plug in the function and the point. Okay, so this is the second definition. This was the first definition, which we already did. Now, limit as h goes to 0. What is f of a plus h? So the function f is the x squared function. And in fact, our point is 3, right? We are finding the derivative. We are finding the slope of the tangent at a equals 3. So we will, let me just do it in steps. We will find f of 3 plus h minus f of 3 divided by h. Okay, so the a in our question, I mean in this formula, the a in this formula is simply the point where we are finding the derivative. Okay, so we should plug in 3 plus h and 3. So what do we find? What is f of 3 plus h? So the f function is the x squared function. And so what should we do? We should square 3 plus h. Should we? So this is supposed to be 3 plus h squared. You don't agree here? Minus 3 squared, okay, which is f of 3. So just evaluate the function at 3, evaluate the function at 3 plus h divided by h. Y squared, okay. Because the function in the question here, it tells us that the function is, I mean, because it is a square function. Okay, we are just plugging this into the function, okay? In the previous one, we also plugged in x and 9. In here, we plugged in x and 9, x and 3. Here we are plugging in 3 plus h and 3. So 3 plus h squared minus 3 squared, okay? So let's do this calculation. So this is equal to limit as h goes to 0. But we have to expand it. So 3 squared is 9 plus 3 times h times 2 will be 6h. So remember, when we square a binomial, we will have 3 terms plus h squared. So these 3 terms will come when you square this expression. Okay? Minus 3 squared, which is 9. So this part is the expansion, I mean the expanded version of this, and this is 3 squared is 9. Okay? And we have h in the denominator. So what cancels out? We have 9 minus 9. So the expression becomes limit as h goes to 0 of 6h plus h squared over h. Okay, can we evaluate this limit? How do you know a equals 3? Good question. So because it is given in the question. Well, we would like to find the derivative at 3. I mean, in the definition, it uses a. Okay, in the definition, when we want to find the derivative at a point a, we just need to plug in that value. So this is the derivative of a function at a. We are finding the derivative of a function at 3. I will just say at 3 instead, okay? So when you are finding the derivative at some point, you should just, a corresponds to that specific point. Okay, so here, now, so the derivative is a. The derivative of the function at a. Okay, so we are finding the derivative of the function at a. In this case, a is 3. Okay, so a represents the point where we are finding the derivative, the slope of the tangent line. Okay. I'm just thinking of a better way to express it. Well, I mean, just think of it like this. x is a variable, right? So x is a variable. So this equation, this formula is written for x equals a. And this question is written for x equals 3. I mean, this question is asking, setting x equal to 3. In this formula, we have x equal to a. So x mean the same thing, the location on the x-axis. So I don't know. And in this formula, we don't have any x here. So we will just, we have just the a value, the value that we are finding the derivative at. And in the question, we are told that it is 3. So, I mean, we will, I think it's going to be more clear once you see more problems. So let's just give yourself some time. I just want to move this. Oops, I didn't mean that. I just wanted to move the whole thing. It's not doing that. Anyways, I want to move it to the left a little. So in here, we cannot plug in 0 immediately because there is h in the denominator. But can we simplify this expression? So can we factor out h? Yes, okay. Divided by h as h goes to 0. So now the h's will cancel out. So we can plug in, yes, we can plug in the limit 6 plus h. And remember, you can plug this value, the limit value, into here whenever it is defined. So which will be 6. Okay, the limit is 6. So find the derivative of f at 2 for the function. Okay, so we will apply the derivative, the definition of derivative. Okay, the derivative of a function at a is the limit, as I'm using the first definition. Okay, we can also use the h definition too, but later, let's save it for later because this is easier. F of a minus f of x. Well, fx minus f of a. Let's do it in that order, although it doesn't matter. Okay, divided by x minus a. Okay, so this is the definition, formal definition of the derivative. And now we should use the value 2, and we should use this function expression, right? So the derivative of f at 2 equals limits as x approaches 2. F of x will be 3x squared minus 4x plus 1, right? This is f of x minus, what is f of a? Let's plug it in. 3 times 2 squared minus 4 times 2 plus 1. So what did we do so far? We just plugged in f of x. We evaluated the function at 2. This is, yes, a equals 2 because we are given it here. And now we will, what should we put in the denominator? X minus 2, right? Okay, so what do we find? What do we find when we evaluate this? 2 squared is 4. 3 times 4 minus 4 times 2 is 8 plus 1. So this is going to be 12 minus 8, which is 4 plus 1, which is 5. So in fact, this is 5, right? So let's write the expression limit as x goes to 2. 3x squared minus 4x plus 1 minus 5. Do you agree? Did I do any mistake? And we are taking the limit as x approaches to 2. So let's write this again. Minus 4 divided by x minus 2. So let's see, we should be able to simplify this expression. So I would just recommend you check out, just review the factoring rules. So you could just use apply the grouping method. 3x plus 2, I believe. So you can just practice this yourself, and when you factor out, I mean, if you just apply, so you will find the grouping number, which is 3 times -4, which is -12, and you would find two numbers whose sum equals -8, whose product equals -12. So you would need to rewrite this expression as 3x squared minus 6x plus 2x minus 4. So once you split the middle term into two terms, you would just group these as the first two and second two, and factor out the common denominator, factor out the common factor, and you will be able to come up with this factored form. So once you do that, you will be able to cancel these out. And let's go back to the blue. So what is this limit as x goes to 2 of 3x plus 2? That's going to be 8. So 3 times 2 plus 2, which is 8. Okay, so what did we find? We found that the derivative of this function at 2 equals 8. Let me also review the slope of the tangent line. So we said that this definition equals the slope of the tangent line of f, like to f at a, which is equivalent to saying this is the derivative of the function at that point. And the new thing that we mentioned about it, but we also say that the instantaneous rates of change of the function f at a. So all these three mean the same thing, and we can just use this formula to find all these three. Okay. So first we want to define derivative as a function. And although you don't like it much, we will need to make use of the second definition of derivative at a point. Okay, so consider this point as a, and consider adding little values to a. So remember, this is how we defined, sorry. Okay, so this is another way of defining the derivative. So how did we define the derivative at this point? The limit as the distance between 2 points approach 0, f of a minus, sorry, let's keep it, f of a minus f of a plus h divided by h. So if you compare the two definitions, again, these mean the same thing. So we talked about defining, we talked about finding the derivative at a point a. Okay, so this is a single point a. So now what we will be doing is that, so consider you might need to evaluate the slope at multiple points, not at a specific point a, but you might need to find this tangent line at multiple points. So why do this evaluation over and over and over? But instead, we will just do this evaluation once instead of a for a general x, and we will come up with some formula for the derivative at any point x. Okay, so instead of generalize, like instead of finding the derivative at a specific point, we will just generalize and obtain a formula for the derivative function. And this is called what we call the derivative function. Okay, so this is the idea. So we will just use the same definition, but not for a specific a. We will write it for x. So let f be a function. So it could be like almost any continuous function. The derivative, yes, f prime is used to denote the derivative. The derivative function denoted by f prime is the function for which this definition, this limit exists. So I'm going to copy the top of the same formula that we have on top. So limit as h goes to 0 of f of, but instead of a, we will just generalize it to any x value, minus f of x divided by h. Well, in fact, I just used the other wrong order here. Maybe I'll just fix that. Oh, sorry. F of a plus h minus f of a divided by h. Okay, so this was the definition for the derivative at a single point. And if you just write this formula, apply this formula for write for x instead of a, then you will obtain a function. So this is the derivative function. So x can mean many points. Well, it means once you have this function, you can evaluate the slope of the tangent line or the derivative at here. You can evaluate the derivative here. You can evaluate it at here by simply plugging in different values for x. Okay, so once you have that formula, you can easily find the derivative at any value you like, instead of doing this calculation over and over for x equals 1, let's say x equals 2, x equals 5, instead of going through it. Yes, instead of doing it specifically for single values, you can just come up with a formula and evaluate at any value. In fact, we will do that soon. So we will develop formulas so you don't need to go through these calculations all the time. Okay, and in fact, there will be tables that lists the derivatives of functions. So it's going to be like, it won't be time consuming to find the derivative. Let's see an example. So the same idea, we will do the same idea. However, instead of a single point, we will obtain the derivative as a formula. And we will use the definition of how we define the derivative of a function, like we define the derivative at a single point. So we will need to use the second definition. And so we evaluate the function at any general x value plus h, minus we will evaluate the function at x and divide it by h. Okay. And now we just need to plug in, so evaluate, plug in the expression for f. Okay, so what should we replace this expression with? What is f of x plus h? So the function f is the square root of x function. F of x plus h means square root of x plus h. Okay, f function is defined as the square root of x. So whatever you give the function as the input, it's going to take its square root. So here in the first case, we just plug in x plus h to this function. So the function will give as the output the square root of x plus h. Here, if you plug in x, it's going to give you square root of x. So let me just show you here, like f of 4 will be square root of 4, which is 2, right? You agree in here? Then f of x plus h will be the square root of x plus h. We are not plugging in numbers, but we are just plugging in that expression, x plus h. So if you plug in x plus h into the function f, then this is what you will find, the square root of x plus h. Okay, and this is f of x. Okay. There is a division by h, and h goes to 0, so we cannot divide by 0, so we have to simplify this expression a little bit. And we did a trick last time, so we multiplied the top and bottom with some expression. Now, so yesterday we talked about some tricks to find such limits, to simplify such expressions. And one of them was to multiply with the conjugate of such expressions. So x plus h inside the square root plus square root of x. So if you multiply and divide by this expression, so let's see what this expression simplifies to. Limit as h goes to 0. Now, so this is the same expression, but in between we have a minus and a plus, right? X plus h inside the square root. So we would need to take the square of the first expression, which is x plus h, and subtract from that the square of the second expression, which is x. Okay? So this is the formula, the difference of squares formula. When you multiply the two conjugates, you take the square of the first, which cancels out. Okay, when you square this expression, and when you square the square root of x, the square and square root cancels out. So we find x plus h minus x divided by h. Okay, so what does this simplify to? Just x plus h minus x over h. So the x's cancel out. So what is this limit? H is cancelled out. Yeah, I forgot something. That's right. I forgot the denominator. So it is in the denominator. Let's put that here. X plus h plus x inside the square root. Let me just add it to here too. Okay, so what now? H is, so the h we have in the top and the bottom will also cancel out. So what do we have? We have 1 over square root of x plus h plus square root of x as h goes to 0. Okay, almost there. We just need to plug in the value of h, right? We just need to evaluate this limit, because we were able to get rid of this problem in the denominator. So we had an h, we had division by 0 in the denominator. Once we got rid of it here, we can now plug 0 in, so the denominator will not be 0 anymore. So what will be the result when we plug in 0 to this expression? 1 over square root of x plus 0 plus square root of x. So what is this? This is 1 over square root of x plus square root of x, which is 1 over 2 times square root of x. Okay, so let me first highlight this. So now we are done. Okay, what did we do? Let's review, no problem. Let's review. We found this is another function, and let me write what function is this. This is the derivative of the function f, and it is this function, 2 times square root of x. Okay, so the function, well, we can say that the derivative of the square root of function is 1 over 2 times square root of x. And so if you want to find the derivative of this function at 1, you can immediately plug in 1 here. So this will be 1 over 2 times square root of 1, which is 1 over 2. So once you know the formula for the derivative, so this is the derivative function. Once you know the formula, you can find the derivative at any point. So I just want to go over different notations we can use for the derivative. So you could see f prime of x. Maybe I'll just note it here. So there, I was going to talk about graphs, but we can talk about them later. So different notations. For the derivative. So this is what we called f prime of x. This denotes the derivative. Another notation is dy over dx. Okay, so where does it come from? So remember the derivative, the derivative is the limit of the slope. So this is the slope, right? This is y. So delta y is the change in y over change in x gives us the slope. And if you just take those points very close to each other, then we find the derivative. And this just denotes, instead of delta, if you put d, it tells you, it just shows you the instantaneous rate of change in the y as you change x. Okay? And another notation is y prime. Because remember, y equals f of x. So we use y and f of x interchangeably. So you can also, this also denotes the derivative of a function. Another notation is d over, so instead of y in here, if you plug in f of x, so in this notation, instead of y, if you plug in f of x, d of this function over dx. So I mean, we will see them in time. You will see different notations in time, but these are all notations used for the derivative. And one last thing I think I would like to say before we go. So we found, for example, that this is the function f, square root of x, and we found another function for its derivative. And if you apply the derivative process, like finding the derivative, if you apply that definition again, you can find the second derivative of this function. I don't know in mine, but we can just find it using the definition. So you can keep finding the derivative of a function. So you can, these are called higher order derivatives, and we will talk about them later.